Hi, today we will learn a purely inductive circuit. When a sinusoidal varying alternating voltage is given to a purely inductive circuit, then a current is generated. So we will be learning today the phase relationship between the voltage and the current. Here you have a purely inductive circuit. So ideally, there should be zero resistance in this inductor. Here you have inductor made out of copper coil. So it is having zero resistance. Now when current is given to this copper coil, the field lines increases. The flux increases through this inductor coil. And due to increase in flux lines, an EMF is induced in the coil, which is back EMF, which will oppose this increase of flux lines as suggested by Faraday's law and Lenz's law. So as per Faraday's law, when there is change in magnetic flux passing through any coil, then an EMF will be induced in the coil, and that EMF is also called back EMF. And as per Faraday law, this back EMF is equal to negative of the rate of change of flux. Now, one more thing. This flux is created due to current flowing through the inductor. So, more the current will be, more will be flux. In other way, you can say that the flux created in the vicinity of inductor coil will be proportional to the current flowing through the inductor coil. And therefore, flux becomes equal to Li. Here L is your inductance and this induction is in the same coil. So this is called self-inductance. When current is changed in a coil and correspondingly the magnetic flux lines also changes through the same coil, then induced current will be there in the same coil by induced EMF, back EMF, which is in opposite direction. So such inductance is called self-inductance. Here the constant of proportionality L is equal to self-inductance. Now in this circuit, resistance is 0 and applied voltage is, instantaneous voltage is given by V is equal to V0 sin omega t, and induced EMF also is there, which is equal to minus from this equation, from equation 1. If we put the value of phi here, then induced EMF comes equal to, from here, minus di upon dt. So these are the two voltages, and resistance in concept offered by a inductor coil is 0. So now from Ohm's law, we know that V is equal to IR, and therefore in place of V, here the voltage supplied to the circuit V0, or better you should say voltage amplitude. This must be said as voltage amplitude. It makes the sense more clear. So V is equal to Vm. Here we should use M. Vm sin omega t and this one more induced EMF in opposite direction. This is your minus L di upon dt is equal to I into R. Here is 0. In inductor, resistance is 0. So this comes equal to 0. Therefore, L di upon dt is equal to Vm sine omega t. And therefore, di upon dt is equal to, let me take L along this side, so Vm upon L sine omega t. Now your alternating current is changing with time. It is time dependent. So when a current is there which is time dependent, and the rate of change of current, that is slope of IT graph. Here IT is time dependent. Therefore, the slope, slope is rate of change of one quantity with respect to other. So the slope of IT graph, here you can see, is a sinusoidal varying quantity. It has a term of sine theta. So the slope of IT graph is sinusoidally varying. So this is the one thing. Now, we are interested to find the current flowing through a purely inductive circuit when voltage is given. So for finding current, we need to integrate this equation. So when this quantity, rate of change of I with respect to t, is added for a time interval dt, then you get this quantity di upon dt, and this quantity, this slope, the rate of change of I with respect to time, when added up to dt time. So you get this quantity. This is equal to Vm upon L sine omega t, and this should also be multiplied by dt. Here dt and dt is cancelled. So therefore, for finding the value of I, the equation given di is equal to Vm upon L sine omega t dt should be integrated. So let me integrate the equation. It implies that I is equal to, this term is your constant. Here this term, this is a constant. So let me take this out of the integration sign and let me integrate sine omega t. So sine omega t is actually minus cos omega t upon omega. Therefore, your instantaneous current I comes equal to minus Vm upon omega L cos omega t. So this is your instantaneous current. Now you know that sine 90 degree minus theta is equal to cos theta. And when you put in minus sign, because here you have a negative sign, so when you put a minus sign on both the sides, then you can find the value of minus cos omega t. And you know that minus of sine theta means fourth quadrant. Here in fourth quadrant, minus of sine theta is negative. This is negative. So therefore, this minus of sine theta actually is sine minus pi by 2. Instead of 90 degree, I am writing pi by 2. and this minus is included here. So minus and minus here, it becomes plus omega t. So in place of minus cos omega t, you may write this quantity in equation this is your equation A. So now in equation A, I is equal to Vm upon L omega sine omega t minus pi by 2. So you can see that we had taken voltage as voltage amplitude sine omega t, and here I has phase angle omega t minus pi by 2. So phase angle differs in the two cases. In the case of voltage, it is a phase 90 degree ahead of the phase of current in an inductor. So what is phase? Let us learn phase. Phase is this angle, the angle with sine. Which determines the value of instantaneous voltage and instantaneous current. So let us see how it determines. So if phase angle is 0, so sine 0 is 0, then instantaneous value of voltage becomes equal to 0. So phase angle has determined the value of instantaneous voltage. Now here in case of current, if you take omega t as 0, so sine minus 90 minus pi by 2, it is in fourth quadrant, so it should have a negative value and with which is equal to minus 1. This is equal to minus 1. So your instantaneous current will become minus Vm upon L omega. So in this way, you can see that the phase angle is the angle which determines the value of instantaneous current and instantaneous voltage. Now, here this quantity Vm, in this equation, Vm upon L omega can be written as Im, where Im is equal to current amplitude if you draw a graph versus V and I, instantaneous voltage and instantaneous current, and omega t, for these two equations, for instantaneous voltage and for instantaneous current. So here we have a coordinate axis, and along y-axis I have taken instantaneous voltage and instantaneous current. Here along x-axis we have omega t. So when omega t is 0, let me draw first of all V versus omega t graph. So when omega t is 0, in this equation, sine 0 is equal to 0. So therefore voltage becomes equal to 0 and you get here 1 point. Now let me take a point which will give us voltage amplitude. So now let us draw V versus omega t graph. When omega t is pi by 2, so sine pi by 2 is equal to 1. Therefore your V becomes equal to Vm only. From this equation, sine pi by 2 is equal to 1 into Vm. This becomes equal to V. Therefore, Therefore, at pi by 2 at 90 degree, you can draw perpendicular from this point and you get a point plotted on this graph. Now, when omega t is equal to pi, so sine pi is equal to 0. The whole term becomes equal to 0. So at pi we get, here for voltage, instantaneous voltage, we get a point over here. Now sine 3 pi by 2. When omega t is 3 pi by 2, that is 270 degree, then sine 270 degree is equal to minus 1. And your voltage becomes equal to minus voltage magnitude. So this is your minus voltage magnitude. At 270 degree, this is your 270 degree or 3 pi by 2, you have voltage amplitude in opposite sense. And finally, in this equation, when sine omega t is sine 2 pi, sine 360 degree, that is again equal to 0 and your V becomes equal to 0. So we get a graph when we draw a line with free hand through all the plotted points. Here we have a graph for voltage versus omega t. Now let us draw a graph for current, instantaneous current versus omega t graph. So firstly we had put omega t as 0 degree. So in this equation now, when you put here at 0, so you are left with sine minus pi by 2 because omega t is 0 and sine minus pi by 2 is actually minus 1. So I comes equal to, from this equation, minus I current amplitude. So if here at this point you have current amplitude Im, and Im should be below, smaller than Vm, because Im is equal to Vm upon R from Ohm's law, and R is a positive quantity. R is greater than 1. Denominator is when greater than 1, then Im should be smaller than Vm. So here we have positive voltage current amplitude, and in just opposite side, here we have negative current amplitude. So first value is your minus Im. Here we get a point, first point. Now when you put in this equation the value of omega t as pi by 2. So pi by 2 minus pi by 2, this becomes equal to 0. And sine 0 is equal to 0. So I becomes 0 when omega t is equal to pi by 2. So when omega t is pi by 2 at this point, your current, instantaneous current, becomes equal to 0. Now next case, when you take omega t as pi, so pi minus pi by 2, you are left with only pi by 2, and sine pi by 2 is equal to 1, and 1 into Im is equal to only Im. So when your omega t is equal to pi, here pi, then current will be your Im. Sine pi by 2, okay, sine pi by 2 is equal to 1, so I is equal to Im. At this point you have value of current as current amplitude. Here you get a point. Now next, when omega t is your 3 pi by 2, this value, next value 3 pi by 2. So when you put here, let me rub these all, erase these all, okay. So here we take omega t as 3 pi by 2 and minus pi by 2. So we get 2 pi by 2 and finally we get sine pi. And sine pi again is 0. So 0 multiplied by Im is equal to 0. So when omega t is your 3 pi by 2, instantaneous current becomes equal to 0. And finally, when omega t is 2 pi, here in place of omega t, you will be writing 2 pi minus pi by 2. So you are left with 3 pi by 2. So 3 pi by 2, this is sine 270 degree, and sine 270 degree is equal to minus 1, and minus 1 multiplied by Im. So your I becomes equal to minus of current amplitude Im. Here you have next point at 2 pi. When omega t is equal to 2 pi, you get a point here. Now let me draw a graph through these points with free hand, and you get this graph. So this is your instantaneous current and instantaneous voltage versus omega t graph. So in a purely inductive circuit, you can see here the diagram between instantaneous current and instantaneous voltage versus omega t. So at value of omega t is equal to pi by 2 here at this point, you will find that instantaneous current becomes equal to 0. It has 0 value. But at same omega t pi by 2, instantaneous voltage becomes highest. It becomes voltage amplitude. Similarly, at omega t equal to pi, instantaneous voltage becomes equal to 0, and here you will find that instantaneous current becomes highest. It becomes current amplitude. So this is the nature of an inductive circuit, a purely inductive circuit in which current lag by pi by 2 in its phase with instantaneous voltage. Inductive circuit. It is inductive reactance which offers resistance to the flow of current. So what is the instantaneous power utilized in overcoming the inductive reactance? So let us find the instantaneous power in an inductor. So power is equal to IV, and your current I is equal to current amplitude sine omega t minus pi by 2, and then voltage. Voltage is your voltage amplitude sine omega t. So this becomes equal to Im Vm, and sine 90 minus theta is equal to actually cos theta. So here with a negative sign, this becomes equal to cos omega t, and this is your already sine omega t. Now when you multiply the quantity by 2 and divide by 2, the power becomes equal to minus Im Vm upon 2 sine 2 omega t. So what is the average power used? In one complete cycle, in one complete time period, for that we will be finding average power. So all the constant quantity should be taken outside of the average term. Here all these are constants, and average of sine 2 omega t. Now the value of sine varies from minus 1 to plus 1. From minus 1 to plus 1, and if you get the average of the two value by adding this and dividing this by 2, you will get 0. So this term becomes equal to 0. Therefore, average power becomes equal to 0 only. So in a purely inductive circuit, power dissipation against the inductive reactance is 0. And this is why in so many places to offer resistance to the current, we do not use resistor. We use any inductor or any capacitor.